As with most industries, energy efficiency is a processing plant priority. A simple way to start saving energy is one that's often overlooked: dirty condensate cleanup. Fact is, condensate systems almost always leak, and condenser heat exchangers are the usual suspects. Leaked coolant can wash iron, copper, and other corrosive contaminants into the process water. And these contaminants not only reduce heat transfer, they promote corrosion and cause further leakage. Old-timers use periodic boiler blowdown procedures to improve water quality, but in today's energy-conscious operations, this option is less than optimal, as it wastes heat and requires significant makeup water. A more cost-effective solution is to polish contaminated condensate for reuse. As more condensate is reused, less makeup water is required, and less makeup water means lower chemical and energy consumption. Used in medium and low-pressure steam plants typical of the food, beverage, and chemical process industries, condensate polishers rely on simple ion exchange technologies to clean up contamination. They're easy to operate, easy to maintain, and as Kevin Pricing of ResChem General Water Services will explain to us now, they're economical to use. Kevin, how about some questions? We've got a lot of them stacked up here. The first one asks, how does a sodium cycle condensate polisher differ from a water softener?
Good question, Jim. Many people are probably more familiar with water softeners than condensate polishers. A sodium cycle condensate polisher is essentially a softener built to operate at a much higher temperature and flow rate. Like a water softener, a condensate polisher uses cation resin in the sodium form, and both systems regenerate using a brine solution. The ion exchange resin in a condensate polisher should have a higher cross-linked polymer backbone, typically above 12%. This allows it to operate flawlessly at 180 Fahrenheit, substantially higher temperature than a conventional water softener. Other than the temperature difference, condensate polisher operates at a much higher flow rate than a comparably sized water softener. For the longest service life, the tanks, valves, piping, and tank internals of the system should be made from 304 or 316 stainless steel wetted parts. Another feature to look for is a subsurface wash, which improves the cleaning performance of the resin during the backwashing of the unit.
Okay, this next one reads, I have a rubber-lined steel tank on my current system. Why are your tanks made in stainless steel?
Good question. We find for smaller diameter tanks below 36 inches in diameter, the rubber lining is difficult, will not be guaranteed by the tank lining shops. We select stainless steel for our tanks because we can ensure a long service life of the condensate polisher.
This next question asks, what is the life of a condensate polisher?
A properly designed, fabricated, and operated condensate polisher should have a life expectancy of 10 to 20 years. The ion exchange resin should be tested approximately every 5 years to ensure the resin is not damaged from excessive heat or heavily fouled from iron.
All right, let's get to our next one. It reads, no capital expenditures are being approved at my plant, regardless of the return on investment. Can condensate polishers be leased or rented?
Good question. While renting is usually not an option, condensate polishers can often be procured under a long-term operating lease, typically 5 years or more. Under the lease option or agreement, the savings per month should be significantly exceed the monthly lease payment, and the leasing company assumes all the maintenance costs for the condensate polisher.
All right, next up, please quantify the plant utility services that are required to operate a condensate polisher.
Good question. Other than the adequate physical floor space to put the equipment, the utility requirements are minimal. Drainage is required to discharge backwash water during the regeneration phase. Separately, the backwash water supply should not be raw condensate, but typically should come from a separate clean source water supply line. The electrical requirements are limited to amount necessary to operate the controller, typically single phase 60 Hertz, 120 volt power supply. The amperage draw associated with the controller will be less than 2 amps. Additional electric requirements will exist should a subsurface wash option be required. However, here too the requirements are minimal with a low pressure air blower, seldom exceeding a horsepower or two.
Okay, here's the next one. You spoke about a subsurface wash. Why is this option important on a condensate polisher?
Condensate polisher acts as both a filter and ion exchange device. The iron corrosion byproduct can exist in a particulate form, which is known as ferric iron, and a dissolved form, ferrous iron. Larger micron sizes of particulate iron will filter out when the top of the resin bed. The subsurface wash acts to remove the particulate iron and corrosion products without backwashing and regenerating the entire resin bed, saving the sodium chloride regenerant and backwash water. The subsurface wash option becomes even more valuable when higher cost regenerant is employed and the resin is run in the amine form.
Okay, what is the advantage of using a sample cooler?
Sample coolers are typically used on both the influent and effluent of a condensate polisher to safely draw samples to prevent scalding of the person taking the sample. Additionally, most commercial available hardness analyzers cannot operate at high temperatures and require the condensate to be cooled to less than 104 Fahrenheit. The final reason to cool the influent condensate is to accurately measure the pH of the influent condensate. In order to control the iron and copper throw from your return condensate piping, it is important to accurately measure the pH of your condensate. Without cooling the influent condensate through an inline sample cooler, the carbon dioxide in the sample will flash off, resulting in a false high pH of your condensate. Since there is a correlation between condensate pH and the amount of iron and copper oxide crud received back in your steam condensate, having a false high pH reading will increase your level of corrosion. In addition, black iron condensate return piping should have a control range of about 8.0 to 8.5. Facilities where neutralizing amines are permitted to be fed in the steam lines, it is important to balance the cost of neutralizing amine and the resulting pH achieved at a given feed rate of the neutralizing amine. Oftentimes, a compromise must be reached between the resulting pH and the amount of neutralizing amine fed to the steam condensate.
Next up we have, what type of instrumentation is used on a polisher?
Since a condensate polisher is acting as an ion exchange device and a filter, pressure differential switches or pressure differential sensors are used to initiate either a full regeneration or just the subsurface wash step in the regeneration. Either a low-cost local controller can be utilized with both a subsurface wash and a pressure differential switch, or a more expensive PLC controller can be utilized. In a facility where an existing DCS system is already in-house and there are additional I/O available, the condensate polisher can be provided without controls. What typically drives the use of a PLC to control the polisher is the ability to view the valve position on the polisher system and to build accompanying shots of the process schematic, including the pressure vessels and the valving on the unit.
Well, Kevin, we'll have to stop there, but I do want to thank you for illustrating once again that it is possible for industry to save money while protecting natural resources. And thanks again for joining us today.
Thank you for having me today.